4.2 is all about looking at these things. Using calculus methods to tell where a function's increasing, decreasing, and then talking about something called concavity, which has to do with how the graph's changing and its general overall shape, okay? So we'll start kind of with increasing and decreasing. We've talked about that before. So the idea is pretty simple. This diagram right here, you're always kind of reading from left to right. So this function would be increasing from there to there, of course. Okay, it just means the y values are getting bigger as we go left to right. This region in here would be constant. What that means is the y value doesn't change. Okay, we've seen that before too, I think. And then you would be increasing again right there. And then you would be decreasing. And decreasing, of course, just means that the graph, the y values are getting smaller like that. So it's a very easy idea what it is. So a couple of definitions. You don't have to know these definitions too much. I talk about this in Calc 2 quite a bit. So a function is said to be monotonic if it's either increasing or decreasing, okay? So like, for instance, if you have some sort of a function that's always going in one direction, and that's kind of the way I think of monotonic, is it's always increasing like that, or it's always decreasing like that. So it's going in one direction, one or the other, okay? So what the definition of increasing and decreasing is basically this. So what we're going to look at in calculus is anytime you have a tangent line that has a positive slope like you have here, you would be increasing. Does that make sense? Okay, got to be going uphill if the rate of change is positive. And then if your tangent lines are negative, like they are here, that would be decreasing. Does that make sense to everybody? Okay, that's what the whole thing that you want to wrap your head around is how the derivative behaves when you're increasing and decreasing. That's the idea. Okay, so one of the things we're going to look at, I'm going to show you this, just load up this little app here real quick, because it's a pretty simple concept. But we can use calculus to determine where things are increasing and where they're decreasing. So this is a GeoGebra app, which they've got a lot of good apps on this. So what this is showing is you can change the function, and it's just going to show the slope of the tangent line. I think things like this are so cool. We didn't have this when I was a college student. So notice right here, we're increasing, right? What do you notice about the tangent line? It's positive, right? So the function's increasing. Now, what would you expect the slope of the tangent line to be right there? Right around 0, okay? Then notice that you have negative slopes of tangent lines like that. So you're decreasing because the rate of change is negative. Then you get back down to 0 roughly there. Then the slopes become positive like that. Okay, so that's the concept. It's a real simple concept on that. And then we're going to look at that a little bit with concavity a little bit later in the section then. So that's the idea, okay? All right, so let's go ahead and let's go to this next page. And I want to go ahead and just kind of work with some examples as we go through this. One thing that you want to be able to do is you want to be able to, if you're given conditions, you want to be able to construct a graph, okay? So let's kind of talk about what this means. So I give you some clues, okay? And you're going to use these clues to come up with a graph. So here's clue number 1. First of all, I'm giving you that the derivative is negative, okay? If the derivative is negative, are we increasing or decreasing? We're decreasing. So we would be decreasing on this interval from negative infinity to 2, okay? That's what that means, okay? Next clue, clue number 2. We're like a mathematical detective, okay? Okay, now if this says f prime of x is greater than 0, what does that mean to you? It's increasing, good, okay? So we have a positive derivative, means we're increasing, okay, like that. Okay, and then if you go to this next one, what does that mean? F prime of x is less than 0. Back to decreasing. Okay, so what we're going to do is we're just going to roughly sketch a graph that would show a function doing this. And there's an infinite number of possibilities to this. So the idea would be that you just sketch a graph. So I'll make like an xy axis here. And let's see, we're going to go from negative infinity to 2. We just want to make sure that the function is decreasing. Okay, like that, I'm going to put a dashed line. That's not a part of my graph. That just helps my thought process. And then from 2 to 5, we're going to be increasing again. And then from 5 to infinity, we're going to be back to decreasing like that. So now you just be creative and you just draw whatever you want to as long as it represents this. So one possibility would be something like this. You would have a function that's decreasing, hits kind of a low point, increases, hits a point like that, and then goes down like that. So that's a real simple idea right there. That would be one possibility, but there's others as well. Okay? All right? So that would be kind of the idea. All right, next one. Let's see kind of what we have here. Now this one, you've got these clues. It says, first of all, that the derivative is undefined. Okay, now tell me what that would mean. If the derivative's undefined, what would that possibly tell you about the graph? Okay, maybe there's a discontinuous. What else? Maybe a sharp point. Okay, someplace where the derivative doesn't exist. Okay, so those are possibilities that we have. Okay, then what does this statement that I just highlighted tell you? They're increasing. Good. Okay. And what does the last statement tell you? We're decreasing, like that. So we just got that extra feature that we're not differentiable at one point. And again, there's more than one possibility on these graphs, so you can be creative, okay? All right, so let's see what we have here. Let's go to -1. We know that where the derivative is undefined. So we'll just say we have no derivative there. Okay, and then when we go to, let's see, if we're past 0, and let's see, greater than 0, no, from negative infinity to -1, this is what I want to write a note to myself is we're increasing, and then when we are from -1 to infinity, then we're decreasing like this, okay? So let's think of a possibility and tell me if this makes sense. Okay, let's increase there, and then let's hit a sharp point, and then let's decrease right there. Okay, would that follow all the conditions of the problem? Yeah, you got a sharp point. Now, you could also make a break there. I mean, you could make the graph do something kind of like this. You could have like, you know, a bubble and do something like that. Same thing, okay, it's increasing, then it's decreasing, but the derivative doesn't exist when x is -1. So there's an infinite number of ways to draw this graph. You just got to come up with something that satisfies the clues I give you. Okay, does that make sense? Okay. All right, very good. Okay, so let's move on from here. Now what we're going to do mostly in this section is we're going to learn, really without a graphing calculator, to analyze a function and just determine where it increases and decreasing. This first one is very obvious because you already know this graph. You already know that's a parabola. But let's look at how the calculus would identify this for us. I mean, if you look at the graph, we're going to be decreasing, and then we're going to be increasing like that. So what you do, if you want to find, look at where a function increases and decreases, the first thing you do is you start by doing the derivative. So we're going to do f prime of x, and that's equal to 2x. Okay, and then we're going to find critical points. Okay, now we talked about critical points. We were doing that a little bit last week. So do you guys remember what a critical point is? It has something to do with the derivative, where it's 0 and or undefined, okay? So that's what you're going to do is find a critical point. So when you find a critical point, always think about where is the derivative undefined or where is it 0. Now that derivative is 2x. That's a line, which is always defined. So what we're going to do is we're just going to set 2x equal to 0, solve that equation, so then you get x equals 0. So that's what your critical point is, and that's how you want to start the problem, is like that, okay? Now, what you do next here is you want to draw what I call a kind of a sign chart. So just draw a number line like that. And what we're going to do is we're going to look at this critical point right here. X equals 0 is the critical point. So that means I'm just going to kind of dash that there. The derivative is equal to 0 right there. That's where the derivative is 0. Okay, now what you do is you take your derivative and you use test points to do this. So give me a number less than 0. Keep it simple for me, -1, okay? So here's what you do. You plug that test point into the derivative. So 2 times -1 is a negative answer. So I just write a bunch of negatives. The reason I do that is because no matter what you pick, as long as it's less than 0, that derivative is going to be negative, right? Okay, I could have done -2, -3, whatever, okay? Okay, let's take a test point that's bigger than 0, like, say, +1. Well, then we would just do the derivative 2 times 1, which gives a positive answer. The reason I put a bunch of positives is just to show you that no matter what you choose, as long as x is bigger than 0, you're positive. Okay, everybody see what I did there? Okay, now that's called a sign chart, which we're going to do a ton in this section and the next couple of sections. So what does this mean right here? If the derivative is negative, what does that tell you about the graph? That it decreases. Good. So we know we're going to decrease there. And then if the derivative is positive, what does that tell you? That we're increasing. Okay, that's what that sign chart does for you, is that. So that means that we can write our conclusion. So this graph has got to decrease from -infinity to 0. And we always use an open interval on that. That's kind of an important thing. The definition of increasing and decreasing means you got to use an open interval, because when you get to 0, you're not increasing or decreasing. That's kind of neutral. That's where the derivative is 0. Okay? And then increasing, we would say 0 to infinity, and then that would be the end of the problem. That's about as easy as it gets. So we're going to do a bunch of problems like that today with all kinds of different functions. Okay? And then graphically, you can tell that this thing is decreasing and then increasing. So you can always check this stuff visually with a graphing calculator if you want to. Okay? All right, does that make sense to everybody so far? Okay, so if I give you a function and I want you to determine the intervals where it increases and decreases without a calculator, find the derivative and find the critical points, and then the third step is to do that sign chart. Then that will give you the answer to the problem. Okay? Okay, let's see what goes on this one now. Now again, I went ahead and just put the graph on there just so that we can verify the calculus we're going to do. So what we're going to do first of all on this is you want to make sure that anytime you got a function, look at the domain. Think about where this is undefined. So clearly, where is 1 over x undefined?
0.
At 0. So that means the domain of this function is -infinity 0 union 0 to infinity. Okay? In other words, just x can't be equal to 0. Okay? So that's an important part of this problem, actually. Okay, so what we're going to do is step 1 is we're going to find the derivative. So I'm going to write this as x to the -1. You don't have to use a quotient rule on that. I see students do it all the time. It's much easier to do it this way, right? And then do a power rule, although the quotient rule works beautifully. So f prime of x is going to be -1 x to the -2. So that's going to be -1 over x to the second. So that's how you want to start, is by doing that derivative. Okay, that's always step 1. All right, next thing we want to do is we want to find the critical points, which I'll abbreviate like that. So what a critical point means is where is the derivative undefined, or where is it 0? Okay, look at the derivative I highlighted. Where is that undefined? It's 0. Okay, so basically you would have that you're undefined at x equals 0. All right, now the next question is the derivative ever equal to 0? Is this thing ever equal to 0? No way. The only way that a fraction can ever be 0 is if the numerator is 0. That's it, period. That numerator is constant, it's -1. And even if you did this, because sometimes students will do this, just not be paying attention, if you set the derivative equal to 0, and if you tried to solve this equation, like by getting rid of the fraction, look what would happen. You'd get some nonsense, right? So the math is going to tell you, okay, there isn't any place where it's equal to 0. Okay, everybody got that? Okay, so now what you do is you want to do a number line, and we're now going to do our sign chart. So what I'm going to do here is our critical point is x equals 0, but this time the derivative's undefined there. So I like, usually if the derivative's undefined, I usually tell students to just put some indicator that the derivative doesn't exist there. Okay, like that. So then what we're going to do is we're going to do test points just like we did before. So we're going to take, like, say, -1 and plug it into the derivative. And a lot of times you can do this in your head. So you would have -1 over -1 squared. What would that be, positive or negative? That'd be negative, right? Because it would really be -1 over 1, right? So that would be negative, like that, okay? Now take a test point that's bigger than 0, like, say, 1. Plug it in again to the derivative, you have -1 over 1 to the second. So what's that, negative or positive? It's negative, right? Okay. Now here's the way I look at this. Now, and I want you guys to be able to do as much of this stuff in your head as you can. See, when I look at this problem, I look at it like this. I know the denominator is always positive. You agree with me on that? Okay. And now I know the numerator is always negative. So isn't that thing always going to be negative? Okay, that's the idea. So you end up having this. So what does this tell you about increasing and decreasing? Decreases, decreases, okay? But you got to break it up into 2 intervals because the derivative doesn't exist there. So you're going to be decreasing from -infinity to 0, and then again from 0 to infinity. If you look at the graph that I did on the calculator, you can tell it's decreasing. Then there's a discontinuity. Then it decreases again, right? Okay, so if you're going from left to right, that graph is always decreasing. So we would write our conclusion like this then. So the critical point was x equals 0, and then we're going to say increasing never. Okay, it never increases, and it decreases from -infinity to 0, and then union 0 to infinity like that. Okay, and you can write it like that. Sometimes I think our textbook will write an interval kind of like this, because what you're doing is you're naming the intervals where it decreases. You can write it either way, okay? Technically, you know, it's either way. I'm used to writing it with a union is the way I do that. Okay, any questions about that? Okay, so the methodology is going to be kind of the same thing as we go through different types of functions. Sometimes they're easy, sometimes they're not so easy. Okay, start with the easy ones first. Okay, so this example, again, we're going to start this exactly the same way. So we're going to start by doing f prime of x. So that derivative is 3x to the second. Okay. Step 2 is to look at finding the critical points. Okay, so we got to figure out where that's 0 or where it's undefined. Okay, so what I'm going to do is I'm going to take the derivative, and I'm going to set that equal to 0, and then that'll give us a critical point. Okay, you can do this in your head. What's x? 0, right. Anything you can do in your head, do in your head. That's important. Okay, so we got x squared equals 0. If you square root both sides, yeah, you get x equals 0. So that would be our only critical point on this particular problem then. Okay, how about this derivative? Is that ever undefined? Now 3x squared is x can be anything, right? Okay, so now we go to doing our sign chart here. So what I do on a sign chart, again, just make a number line, put your critical point here, x equals 0. Now the derivative does exist there, it's just equal to 0. Okay, like that. Okay, sometimes I write a note to myself just saying f prime of x is 0. But if it's undefined, I like to write a note to myself like that. Okay, now it's the same idea. Use a test point. Okay, for variety, let's you do -2 this time. It doesn't matter. So plug it in, and what kind of value do you get when you do 3 times -2 to the second? You get positive, right? Okay, so that's always positive. How about if you go out here? Is it going to make any difference? Still positive, isn't it? Okay, so pick a number bigger than 0, plug it into the derivative. That's always positive. Now, let me ask you a question. Would you guys have known just by looking that's always positive? I hope so. How come? Because it's x squared. Okay, so it is always positive. Okay, except for that one place where the derivative is equal to 0. So that means that you're going to increase there. The function's increasing, then the function's increasing more, like that. Okay, so that means the conclusion for increasing is going to be -infinity to 0 union, and then 0 to infinity like that. The reason that I don't include 0 is because the derivative is equal to 0 there. So you have to break that up into two intervals. It would be wrong to say it's increasing always. That's not true, because at this point right here, isn't the tangent line equal to 0? Okay, so there's two, you have to kind of break that down into two intervals. So you can tell the graph's increasing, then it hits a level point, then it increases more. That's what happens, okay, if you do that. Okay, decreases, it never does. So that would be the solution to that problem, okay? Okay, the three examples I've done so far are not too bad. That's real straightforward. They get a little bit heavier into the algebra as we go. So is there any questions about anything so far then? Okay, all right. It's all about finding critical points, sign chart, analyze that sign chart. Okay, that'll tell you where you're increasing and decreasing. Okay, now this thing that I'm saying down here, this is just sort of a point that I'm making, is when you get a critical point, sometimes students are thinking that's a minimum or a maximum, and that's not always the case. So like if you look at the problem we just did, that critical point right there is not a max or min, is it? What a minimum is, like if you have a local minimum, it means the graph has to decrease, then it has to change directions and increase. Okay, so that sign chart is going to have to change signs in order to have some sort of a extrema. If you had a maximum, then the graph would have to do this. It would have to increase, then it would have to change directions and decrease like that. Okay, so just because you have a critical point, that doesn't mean you have a max or min. Does that make sense? Okay, all right, so that's pretty important. Okay, the other thing is, here's another possibility. You could have a derivative that's undefined. Like for instance, if you look at this graph, if you did a tangent line right there, wouldn't the tangent line be vertical? What's the slope of a vertical line? There isn't one, exactly. So that one, again, you could have a critical point that doesn't exist, or it's a place where the derivative is undefined, but that doesn't mean it's a max or min. That's what the point is I'm trying to make on that. Okay, so this diagram right here just kind of illustrates what we've already been doing. So what would happen on this graph if you made a sign chart? You would have a positive derivative there because you're increasing, correct? Okay. Here you would have a negative derivative until you get to that point right there. That's because you're decreasing. Okay. Then you would start having a positive derivative again. Then you would level off where you have a zero slope, and then you would be positive again. So if you did a sign chart on this problem, it would go positive, negative, positive, positive. That's how that would go. So you want to be able to tell from a graph how the sign chart would even look. Okay, that's pretty important. Okay, all right. Let's move on from that point then. Any questions about anything so far? Okay. Now, some of these get a little bit more complicated as we go. And, you know, when you get into logarithms and all the different functions that we've learned how to differentiate, sometimes it can get pretty complicated with the algebra. So this one's a little more involved in this one. So, again, what we're going to do with this one is, and I'm going to do my derivative over here so I can take up a little bit of room, or let's do it kind of down in this direction here. So, start by doing f prime of x, which is a nice simple derivative. So that is 4x to the third minus 12x to the second plus 8x like that. Okay, step 2, find the critical points. Okay, two things. Is this derivative, tell me if this derivative is ever undefined. No, that's a polynomial, right? X can be anything. There's no zero denominator or anything. So what we want to do when we do the critical points is we got to go dig into our algebra background a little bit. So what we're going to do is take this derivative and we're going to set that equal to 0. Okay, like that. All right, now we got to dig into our background. How do you solve an equation like that? It's factoring, right? It's all about factoring. Now, one thing I would do is it looks like you have a common factor of 4, so you can pull that out, but you also have a common factor of x, right? Go with the lowest exponent. So you're going to be heavy into factoring when you start doing these problems. That may be something you may have to review a little bit. So that's x squared minus 3x plus 2 like that. Okay? Now this thing still factors, doesn't it? Okay? If it didn't factor, it's quadratic, so you'd have to work out something with the quadratic formula. So most of these things are kind of designed so they'll factor. So we're going to go ahead and factor that. So that would be x times x to get x squared. You'd have 2 times 1 to get 2. And then how do the signs go if you make the inner and outer add up to negative 3?
Both negative.
Both negative, right. Okay. So make sure that you're solid on the factoring. And it's always important when you do these problems, before you move on, make sure you factored right. Check it. Multiply it out. Make sure it's right. Okay. So now, when you solve this equation, this is kind of stuff you do in intermediate algebra or college algebra or something, you have 3 factors. So you set that factor to 0, this factor to 0, and this factor to 0. So you're going to solve those 3 equations. And all those you can do in your head. So what are the solutions? What are the 3 solutions? 0, 2, and 1, right? Okay. Do that in your head. You don't have to show that unless you need to. So that means your critical points occur at x equals 0, x equals 1, and x equals 2. Okay, so that's what we've accomplished by that. Okay. Okay, so once you've got your critical points, and that's doing the derivative, setting it equal to 0, then you want to go ahead and put together your sign chart. Okay. So what I'm going to do on this is we're going to break this up. We got a 0, got a 1, and then we got a 2. Okay, like that. So we're going to break this up into regions to analyze where it increases and decreases. Okay. Now, what I like to do on this is you got 2 choices. When you do test points, you can either plug in there, or not there, into the derivative. So where's my derivative? Which is, the derivative's here. Okay, yeah, this is my derivative. You can plug in there, or you can plug in here. Now, personally, for me, I find it easier to work with the factored form. That's me. I think you will too in the long run as well. So what I'm going to do, I'm going to write down f prime of x after we factored it was 4x, x minus 2, x minus 1. And then we're going to analyze the sign chart. And try to do as much of this in your head as you possibly can, because it'll help you. So I'm going to start with a test point of -1 there. Pick a number less than -1. What I'm going to do is I'm going to plug in here, okay? And I'm just going to try to write this in here. I'm going to do a lot of this in my head. Okay, if you do 4 times -1, what kind of number do you get for 4 times -1? You get a negative, right? So I'm just going to put a negative there. Okay, what if we do -1 minus 2? What's -1 minus 2? That's also negative, isn't it? Okay. How about if you do -1 minus 1?
Also negative.
Is that negative? Okay. Now, if you can't do that in your head, just write it out. All I'm doing really is I'm doing this. Okay, and I'm just looking at, okay, that's negative, that's negative, that's negative. So a negative times a negative times a negative is a negative then. So that means that result's negative, which tells me that the function's decreasing. Okay, everybody see what I did? Okay, and just move on and do the same thing over and over and over again. Okay, so I'm going to start it again. Okay, so let's take something here. You can use decimals, you can use fractions. I'm going to use a fraction. I'm going to use 1/2. Okay, and the thing about it is you don't have to really crunch this out. All you got to figure out is it positive or negative? So I'm going to go to this derivative, and I'm going to do 4 times 1/2 times 1/2 minus 2 times 1/2 minus 1. See, what I see students do all the time, and it's a total waste of time, is go ahead and just crunch that out and get an answer. Don't do that. What is this, positive or negative?
Negative.
Negative. What's that? Negative. What's that? So you have a positive times a negative times a negative. That's all you got to do. Okay? Then you got your result C. Okay? That's what's important, is just do it to that extent, and then you'll be good. So this one you have like a positive times a negative times a negative. That's a positive result. So that means the function is now increasing like that. Okay? So we got that. All right, and let's move on from here to the next piece. Let's go, say like 1.5, okay, or something. You can use a decimal if you want to. Then it's the same thing. You're going to do 4 times 1.5, 1.5 minus 2, and then 1.5 minus 1. Any of that you can do in your head, just do it in your head. What you have here is you have a positive, you have a negative, and you have a positive. So that's positive times positive. So what's that? Negative means you're back to decreasing again like that. Okay? And if you did the last one, what would happen if you did the last one? If you used a test point like 3, you would end up with all positives. Okay, if you go through the details. So if you do that, then you'd be back to increasing. Does everybody understand what I'm doing? I'm getting those results. Okay? Doesn't matter what the test point is, as long as it's within the interval. So then we're ready to write our conclusion. So we're increasing in these two places. Okay, so that's going to be between 0 and 1. We're increasing. And then from 2 to infinity, we're also increasing like that. So you're generally going to write that in interval notation. Okay, decreasing is going to be in these two places here. So that's going to be negative infinity to 0, and then 1 to 2 like that. So that's the idea, okay? Now, remember, we're learning calculus in here, so I mean, you might think, well, all I got to do is get my graphing calculator out and I can answer it. Yeah, you can. You want to use the graph to help you understand the connection between the calculus, because if I look at this graph I provided, all I've got here is I have a negative derivative, then I have a positive, then a negative, then a positive. Everybody see that okay? Okay. Already know how the tangent lines slope, so that's what the sign chart did for you, is that. Okay? All right, is there any questions about that? That's still not too difficult if you've got the algebra down. And then the next one I think's got a logarithm, so you got to work with derivatives of logarithms on that one. Okay? Pretty straightforward. Excellent test question, by the way, in the future. That's pretty straightforward. Factoring, kind of a nice thing to be able to do without a calculator, okay? Okay, let's look at next example. Okay, so this time I'm going to go ahead and let's start with the derivative and kind of see if we're on track with this. Okay, if you do a derivative on this, what kind of rule are you going to use? Got to use a product rule right there, don't you? You have x squared and ln of x squared, okay, first and second. And then the derivative of 1 is 0. So what you're going to have is you're going to do the first, which is x squared. Then you're going to multiply by the derivative, which you can do in your head if you want to, ln x squared, plus the second, times the derivative of the first. And then the derivative of 1 is 0, so you don't have to put that 0 there. I'm just doing that for emphasis. So we need to focus on the derivative first of all and get that going, okay? All right, so let's see what we have. This would be x squared. Okay, tell me what the derivative of ln of x squared is in your head. 1 over x squared times 2x, right? Okay, remember when you're doing an ln, it's always 1 over the function times the derivative of that function, which the derivative of x squared is 2x. Okay, like that, okay? Now you move on to the next part. You're going to just bring down the ln x squared, and of course the derivative of x squared is going to be 2x, like that. Okay, so that's the derivative in an unsimplified form. So when I do this, it looks like that's going to cancel. That's going to leave 2x there. Okay, then I'm going to end up with, that is, hold on, did I write that?
You just missed an x after your ln.
What did I do? Oh, I see what I did. I didn't write that down right. Okay. Yeah, okay. ln, that should be ln. Whoa, what did I just do? I didn't write it right. Because the second one is ln x squared, right? Is that better? Yeah, okay. All right, so I've got ln x squared here, and then the derivative of x squared is 2x. So this derivative is 2x ln x squared. Now I've got it. Okay, so I'm going to be careful about where you put that square. Okay, so that requires a product rule. Now what we're going to do is we're going to do the critical points, okay, on this. So when I do the critical points, okay, I need to set this equal to 0. This is our derivative. That's what we're going to analyze, and we need to set that equal to 0. Now let me ask a question on this. These are kind of important things. Is this derivative ever undefined?
No.
No is the right answer, okay? Remember an ln, when you do an ln, this is something that you don't want to overlook. When you do an ln, you have to do an ln of a positive number, correct? Okay? And you can never do the ln of a negative number, but the other thing is you can't do ln of 0, okay? So actually, this thing is undefined at one place, at 0, okay? So you do have a critical point at 0 there, right? Okay, because again, if x is 0, then you're going to end up doing the ln of 0. Okay, does everybody see that? You've got to pay attention to that. That's one of the most common things in these problems that students forget about, is the fact that the derivative can be 0 or can be undefined somewhere. So you would definitely have a critical point at 0. Then the other thing you need to do is you need to take the derivative that we got, and then you need to set this equal to 0, and then you need to solve that equation. Okay, everybody with me? Okay, how do you solve an equation like this? What do you think? Factor. Okay, you're going to factor over and over and over again. Okay, you set it equal to 0. This has a common factor of 2x. So taking 2x out, that will leave you 1 plus ln x squared is equal to 0 like that. Okay, so then what we end up having on this then is you're going to set each factor equal to 0. So you've got that. Okay, and then the next thing on this one is, let's see, we're going to do 1 plus ln x squared equals 0 like that. Okay. All right, so what we would have here then is you would have divide by 2, so that gives x equals 0. Okay, that's part of the solution to that. And then when you do this one, now see, this is where you get into logarithms now, and sometimes students struggle with this. If you solve an equation with a logarithm, you want to have the logarithm isolated, right? Need to have that. Then, what do you do when you have an equation like this? You write it in exponential form. So the base of ln is e. How do you write that in exponential form?
2ln.
You would say e to the negative 1 equals x squared, correct? Okay, let's write that down, see if it takes us anywhere. Okay, so we'd end up having e to the negative 1 is equal to x squared like that then. Okay? Now, what I'm going to do on this is you could change this to 1 over e to the first, right? Then you would have here, you would have x squared. Okay, is everybody following that okay? Because you're going to deal with exponential and logarithmic equations. That's one of the reasons you learn it, like in college algebra, okay? So now what do we do?
Square root both sides.
Square both sides. Notice I got a plus or minus. That's important, okay? So you have x is equal to plus or minus 1 over square root of e. Now you can do the square root of 1 and the square root of e separately. So the 1 comes out of the radical. So I'm going to write this just as plus or minus 1 over square root of e like that. Okay? So here's kind of what we have here. All right, what we have is for our critical points, it looks like we have these things. We have 1 over root e. We have negative 1 over root e. Those are places where the derivative is 0. Okay? Then what we have here is we also have 0 as that critical point right there. So we've got all of our critical points. What makes this more complicated for students mostly is all of this stuff right here because you're working with a logarithm. Yes?
Because it's an ln, we can bring an exponent to the front with 2 and then divide by 2ln.
Okay, tell me which part you're on here. You may have to come up and point out to me so I can tell.
At this point, right here, bring this forward and then divide by
Yes.
2ln and be -1 over 2ln.
You could, but the reason you wouldn't want to do that is because you want to write it in exponential form. If you brought the 2 down, then you could not write that in exponential form. So what you want to have is you want to have a logarithm with nothing in front of it. Then you're just going to go e to the -1 equals x squared. Doing that would not allow you to do this. So you always want ln to be isolated with nothing in front. Bingo, that's why. Okay, does that make sense? Okay. Right, so now what we do is we got to do a sign chart on this one. This gets a little messy because you've got these irrational numbers with the e on it here. So let's go ahead like we've been doing, and we're going to draw a number line, okay, like this, and we're going to put down our points here. So we have like -1 over root e, we have 0, and we have 1 over root e like that then. And then we're going to basically go through and analyze the everything on this then. So we're going to look at doing critical points and plugging them in. Okay, so what we got to do on this now is you got to go back to the derivative. You got to keep track of everything on these problems. So that's our derivative right there. We also have the factored form of the derivative right here, and that's what I'm going to use. Is I'm going to, as I analyze with test points, I'm going to use this 2x times 1 plus ln x squared. Now remember, you don't have to crunch out everything. You just got to tell if it's positive or negative. Okay. Well, one thing that would probably help a little bit on this, it might be useful to at least do this one thing on your calculator. If I did like -1, -1, and then divided that by square root of e, and you got an e like on right above the division symbol. So I could go like second division symbol to get that to come out. Okay. So it might be useful in this case. So this is, I'm going to write a little note to myself that this is really about -0.6. This is actually going to end up being positive 0.6. Okay, that'll be helpful to you. Okay, so now let's figure this out. Now you can use whatever you want to. I'm going to use, like for my test point here, I'm going to use something like -2. Okay, or whatever. As long as it's less than -0.6, you're good. So if I plug it in, I would have, and take that -2, plug it in for x, we'd have 2 times -2, and then 1 plus ln of -2 squared. Okay, and just write it down and think in your mind if that's positive or negative. Don't go jumping for your calculator on this, because you'll get more out of it if you analyze it in your head. So here's the way I look at this. This right here is negative, right? Agree? Okay. Now, how about this? What you're doing here is you're doing 1 plus ln of 4. What is that whole thing? Positive. Okay, if you do a logarithm of a number, let me show you something about a logarithm graph here, just to kind of review this real quick. If I put in a graph of a natural logarithm and just did that in the standard window, this is kind of what's important. Whenever you're doing a logarithm of a number bigger than 1, don't you have positive results? Okay. And if you have a logarithm of numbers between 0 and 1, you have negative results. Okay. And that's a real important thing to understand about that logarithm graph, is that. Okay. So anytime you're doing a logarithm of a number past 1, you have a positive, and otherwise it's negative. So that means that since ln of 4 is positive, that's positive, so you have a negative times a positive, which means that's negative, and that means you're decreasing. Okay? Now see, if you have the knowledge of how that logarithm graph goes, then you don't have to go looking for your calculator. Does that make any sense? Okay? All right. So let's move on from here. So next thing let's look at is, let's say, what's a good test point in here? What do you think? I don't care. -0.2. How about something like that? Doesn't matter as long as it's in there. Okay, it's less than 0 and it's bigger than -0.6 approximately. Okay, so let's do this again. So we're going to do 2 times negative 0.2. Then we're going to do 1 plus ln of negative 0.2 squared, like that. Okay? So let's see what we have. Don't crunch it out. Don't grab your calculator. What's this right here? Positive or negative? Negative. Okay? Now let's see if we can do this in our head now. What's that? Positive or negative?
Positive.
Now here's how I know. And this is what you want to do when you're doing this problem. Okay? When you do this, isn't x always going to end up being a positive number? Okay? The thing is right there, you want to make sure that you see what you're taking a logarithm of there. Okay, so if you do 0.2 squared, you're going to end up being in one of these places right here, okay, where it's negative. Okay, that thing right there is some negative value. When you get to that, you might want it to be safe. You might want to go to your calculator on this. This is a problem that's kind of nicely suited for a calculator. So what I'm going to do here is I'm just going to make sure I'm going to do this. So if I do the ln of, and I'll do this like this, negative 0.2 squared, well, not like that, like this. So ln of parenthesis negative 0.2, now I think I got it right, and then parenthesis, then square it. Okay, what that's doing is, what did I do wrong there?
You can just put 0.04.
Because you have to actually square that.
Oh, you're right. Yeah, you're right. So I need to go like this. I need to go negative 0.2 like that and get that squared. Go like that. So that's a positive number. Now that's going to have a negative result. So if you do the ln of 0.04, then you're going to get a negative result. Okay? But the value of that's negative 0.3, so that means that what you're going to have here is you're really going to have 1 minus about 3. Okay, so you're going to have a negative times a negative, so that means you're going to end up being positive in there, like that. So that means you're going to increase like that. So sometimes you're going to need to get your calculator out when you have these irrational numbers and see what happens. Okay, now by the same argument, if you went like this, if you put in like 0.2, and if you did that, you would end up now, if you did 0.2, it would go kind of like this. Okay, now this one you can do in your head. Okay, so I've got 2 times 0.2, and then I've got ln of 0.2 squared. Okay, that right there is positive. And then this thing right here, you're going to have the same thing, right? That's going to be negative again, because that's going to be ln of 0.04, which is negative 3, like we did before. So that means that's going to be negative there, and then that's going to decrease like that. Okay? So if you're not sure, get your calculator out and crunch it out. And then the last one, let's take a number bigger than 0.6. Let's take, like, say, positive 2. Okay, if you did that, and if you worked out the details on this, I'm not going to go through all the details because it's a little time consuming, but if you plugged in positive 2 into this derivative, you would get a positive answer like that. Okay? All right, so what we would have then for our conclusion is we would be increasing on these two regions. We would go negative 1 over root e to 0, so we'd be in there. And then we would go 0 to infinity like that. So that would be how that increases. For decreasing, it would be in there and it would be in there. So we would say negative infinity to negative 1 over root e. Okay, and then the other one would be 0 to root e like that. 0 to 1 over root e like that. One thing that I do on my sign chart too, because you gotta pay attention to this when you do this, is this is just my method. I always put a box around the test points so that when I write my intervals, I don't get confused. I'm using the critical points on my interval. Does that make sense?
Shouldn't your second increasing be positive 1 over root e to
Oh yeah, right. The increases would be there to there, right? So change that to 1 over root e. Then I think I'm okay, all right? Yeah, Yeah, I'm good from there. Okay? Right? Sometimes when you get that sign chart, you got to make sure that you're reading the critical points correct. And then this would be, yeah, like you said, 1 over root e like that. Okay, that's the answer. Okay, see, that one's a little more complicated, isn't it? But if you have technology, then you can use that to help you with that sign chart anyway. Okay? So that would be kind of the idea. Okay, let's move on to this next page. Is there any question about anything I did with, mainly the hardest part of this problem for most students is this right here, is the algebra part. Does that look okay to everybody? Okay, and like I say, when you get into, once you get those critical points, if you need to use your calculator to help you a little bit, do that, you know, because you might have to think about using your calculator a little bit on some of these. Okay, let's see. Let me erase the mess I've got on this problem. Let's go through. Let's do one more of these. Let's just do this page, and then we'll take a break. So let's do one that's got a trig equation in it. And then this is another thing. Sometimes students struggle a little bit with the ones that have trig in it. So this is cosine squared of x. Now, I put this in my graphing calculator, and we'll do that in just a minute together. That's what a cosine squared of x is. What did that square do to the basic cosine? Well, look at the graph. What kind of y values do you always have? Positive. See, if you square a cosine, if you do a cosine can have negative and positive numbers, right? Okay. It just, you know what happened really is it did this. Okay, like this is a cosine, and then this part right here, you know what happened to that? It just became positive values. That's really what happened when you did that. Now, it did change these values too because they're all being squared, but I kind of think of it as the regions below became positive values because you squared them. Okay, that's where that comes from. Okay, so let's go ahead and let's work on the calculus. So we're doing all these problems exactly the same way. Step one is you need to work with your derivative. Okay. Well, okay, when you do something like this now, it's probably good to write this as cosine of x squared, and then we want to do that derivative. So what rule applies to this derivative? Chain rule. Bring the 2 down like that, okay? So you're going to bring the 2 down. So that's going to be 2 times the cosine of x. Then the chain rule says multiply by the derivative of what's inside, which you can do in your head if you want to. So that's going to be 2 cosine x, and then the derivative of cosine is what? Negative sine x. So you're going to end up with negative 2 cosine x times sine x like that. Okay, then we've got to think about what we're going to do with that derivative. Now you got to start thinking about trig identities because they come in handy a lot of times on these problems. So this would be something that's always defined. Okay, the sine of x and cosine x are always defined. So you're going to need to go ahead when you do your critical point. You need to go ahead and set that derivative like that equal to 0. So you got to solve that. Okay. Now, what you can do in a problem like this is there's several approaches that you can take on this. I think what I'll do is just do like an identity here. And there is an identity that goes along with this. Or you could even look at this. This thing's already kind of in a factored form because cosine is a factor and sine's a factor. So you could set each factor equal to 0. But what you're going to end up having is you're going to have kind of an infinite number of critical points, right? Okay, and the critical points, if you look at your graph, are all going to be here, aren't they? They're going to be all those places where the tangent line is 0. Agreed? Okay, so we're going to have an infinite number of those things. So actually what you can do on this one is you can disregard the negative 2. You could divide by negative 2 if you want to. I'm just going to do it this way. So I've got cosine x times sine x is equal to 0. Okay, like that. Now, these basically are factored already, so what we could go through and do on this is we could just set cosine x equals 0, and solve that equation. And then we could set sine x equals 0, and then we could solve that equation. Okay, like that. Okay, that's because they're multiplied and they're a factor. So what would come in handy on this is basically just the unit circle. So I'm going to look at these key points on the unit circle that hopefully you remember to help us solve this equation and put this together with, when we got to kind of do this with a formula. Okay, so we would have that. Okay, so the unit circle will tell us the solutions of these equations. So what are the angles where the cosine is 0 on a unit circle? Just the two angles.
Pi over 2.
Pi over 2,
3 pi over
3 pi over 2, then you can go to the negatives, can't you? Okay, all right, all right. So what you'll have here is, let's just kind of write this out. We have x is equal to pi over 2, 3 pi over 2, then we would have like negative pi over 2, like that. And then we'd have negative 3 pi over 2, kind of like that, and so forth. Okay, so you would end up having that, like this. And then if you go to the sine, okay, where is the sine equal to 0?
0 and pi.
0 and pi, right? Okay, so what you would end up having here is you'd have like 0 and pi, and then you'd have like negative pi, and then you could go all the way to 2 pi, and so forth, kind of out like that then. Okay, so that's what you would end up having on that then. Now, let's go ahead. If you brought your graphing calculator, let's go ahead and do something with the calculator on this before we finish this, because I want to show you a couple of things. So let's see, we're graphing, we want to graph the cosine squared of x. So a couple of things you want to do. You want to make sure you're in radian mode. Okay, like that. Get yourself in radian mode. And when you put a cosine squared in, depending on your calculator, I usually just put it in as cosine of x, like that. The whole thing has to be in parentheses and then squared like that. So it's got to be don't put in cosine x to the second. It's the whole thing to the second. So you want to make sure you have that. Now let's do just kind of a standard window, just from negative 2 pi to 2 pi. So if you press your window button, let's go negative 2 pi, like that, and then let's go to 2 pi, like that, just kind of looking at a lap around the circle. It doesn't matter what the scale is, but I'm going to go ahead and have you put in pi over 2 like that. And then that'll change that to whatever that is, 1.5 or something like that. Okay? And then for the y's, you could go negative 1 to 1. I'm going to expand it a little bit and maybe go negative 2 to 2 like that. And then you can graph that. And I'm going to move this over here so you can look at this if you need to. Okay, here we go. I'll put that over there. Okay, and then if you do your graph, you'll kind of see everything goes above the x-axis like this. The reason I want to kind of show you guys this too is when you're doing your homework, you want to do this as calculator free as possible, but you also want to take advantage of the technology, and you want to make sure that everything looks good to you then. Okay, so here's what we have. Notice on here, if you traced, like look at these solutions over here. If you traced at 0, well, obviously that's a critical point, right? Okay, if you trace at pi on this, so if I just now press pi in, then you get a critical point and so forth. Okay, you agree? Okay, what are our other ones? The other ones were like pi over 2, 3 pi over 2, and so forth. So if you traced at pi over 2, okay, well, that's another critical point. So see, what's happening is these minimums are these values right here. And these maximums are these values right here. Does that make sense? Because all I'm trying to show you is to verify these critical points graphically. So that verifies what we just did. Okay? So what we're going to do now is we're not going to write all these critical points because there's an infinite number of them. So what we're going to do is write a formula. This is something you did quite a bit in trig when you did asymptotes. Remember, you did k pi and all that kind of stuff. Okay, so we got to do that. All right, so let's look at what the formula is for this. Okay, in terms of k and pi, do you know what that formula would be for this over here? K pi, right. And what would k be? An integer, good. So k is an integer. If you don't know this symbol, it's a good thing to learn now. When I say k is an integer, you can say ke. That means it's a member, it's an element of, and that funky little z is the symbol for integer. And what an integer is numbers on the number line. 0, 1, 2, 3, -1, -2, so forth like that. Okay? Now what is the formula over here?
Pi over 2 plus k.
Okay, k pi over 2, right? Okay, what k is k is the number that's in front of pi over 2. But what kind of number is that? It's not just an integer. What is it? 1 pi, 3 pi, 5 pi, 7 pi. What kind of pi? Odd pi, right? Every odd, right. Okay, so what you would say here, I don't have a symbol I'm going to use for that, so I'm just going to say x is a odd integer, like that. Okay? So you have to write a formula, okay? And you would have done this a little bit in trig. It kind of depends on when you took it, you know, and whether how much your teacher emphasized that. So what we're going to say on the critical points is, yeah, you got to write it as a formula. So you got to say x is equal to k pi over 2, and then you have to say k is an odd integer. You have to say that or you're wrong, okay? Then you also say x is equal to k pi, and then you say k is an integer, or you can use that symbol if you want to, like that. So there's an infinite number of critical points on this graph. Does that make sense? Okay? And see, the more of these things you write out, the easier it is to find that pattern. This one's just 1 pi, 2 pi, 3 pi, and so forth. So it's k pi. Is that clear?
Wouldn't it be k is odd integer, not x is odd integer?
On which one?
On the cosine?
Over here? What are you thinking again?
Wouldn't it be k is an odd integer, not x?
Yes, thank you. I don't know why I put that. So I put it right here, but I put it wrong there. Thank you. Yeah, that right there should say k is an odd integer. Okay, so we're good. Okay, now really on a problem like this, when you do your sign chart, you could, you know, it's once you see how the graph goes, and I'm going to basically just do this one kind of a miniature sign chart. You don't have to do all this. All we're going to do is kind of do something like this. So let's draw a number line. And since the function's periodic, once you figure out 2 intervals, then you'll have the rest of it made. You don't have to do like a million intervals, because it's just going to go plus, minus, plus, minus, plus, minus over and over and over again. So let's keep it simple. Let's start with this critical point of x equals 0. Okay, then let's go to this critical point, which is x equals pi over 2. And then let's go to this next critical point, which is pi. And that's good enough because it's going to alternate over and over and over again. Okay, so let's do, let's write down the derivative. So let's see, the derivative was negative cosine of 2x. So I'm going to write down negative cosine of 2x, or no, negative cosine x sine of 2x, like that. Okay? So we're going to use test points here. Okay? Now you can use whatever you want to. Pi over 2 is about 1.5. And you can use anything. You can go to a unit circle. I would recommend you just think about the unit circle. How about pi over 4 as a test point? Is that logical? Yeah, okay. And the other reason I'm doing pi over 4 is, do you guys remember what the cosine of pi over 4 is? Root 2 over 2. How about the sine of pi over 4? I'm just using something that I know, okay? That's what's helping me. So if I plug that in, I have negative 2 cosine pi over 4 sine pi over 4, okay? But, you know, you don't even have to deal with the square root of 2. All you got to know is this. I want you to think about this. If you're in quadrant 1, which you're in quadrant 1, agreed? Okay, what is the value of the cosine of any quadrant 1 angle, positive or negative? Positive. How about the sine of any quadrant 1 angle? Okay, so what you would have is a negative, you would have a negative 2 times a positive number times a positive number, so it's negative, so that means that we're decreasing. So you may remember, teachers teach this different ways. One way that I've taught this in the past is all students take calculus, all science teachers crazy, or all strippers take cash. Those are my 3. Okay, take your pick. So everything's positive in quadrant 1. Okay, all right. Now we go to see, this is quadrant 1. Now we're in quadrant 2 because we're between pi over 2 and pi, right? Okay, so we have a negative 2. Now let's see if we remember any of this stuff or not. If the cosine of quadrant 2, what are you, positive or negative? You're negative. How come? Cosine's x over r. X is negative in quadrant 2. Okay, so you're going to have a negative there. How about the sine of a quadrant 2 angle? Positive. There you go. See, all this stuff starts coming in handy, doesn't it? So we have a negative times a negative times a positive. That's a positive. So that means the function's increasing. Now you could use the square root of 2 over 2 and that kind of stuff, but you're spending time. So to me, go back to thinking about what you learned in trig with everything. Okay, so here's what happens then. What you're going to do, and I'm going to just kind of refer to this graph to help us, you're going to know basically this sign chart's going to over and over again just go negative, positive, forever and ever and ever, right? So if you look at what we have, is you're going to have a pattern on this. This thing is going to decrease like this. I'm just going to shade those places where it decreases and write down a few intervals. And we have to write this with a formula. So that is 0 to pi over 2. Okay, this is going to be back to pi to 3 pi over 2, like that. So that's where it's decreasing. And then if you go over here, that's negative pi over 2. This is negative pi, so you'd be decreasing there. And then this is negative 3 pi over 2. And then this is negative 2 pi, like that, and so forth. Okay, so let's see if we see a pattern on this. Okay, let's look at it. 0 to pi, pi to 3 pi over 2, negative pi over 2 to pi over 2, and so forth like that. Now, we're not going to really write a formula on this. The way I'm going to do on this is we're just going to write a pattern and kind of use some dots, dot, 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 to show the pattern. So let's just kind of write down some of these. We would have decreasing, we would have like 0 to pi over 2. And then you could do a union or you could do a semicolon. Then we go pi to 3 pi over 2. And then you can just go dot, dot, dot. Okay, like that. Okay? And then do some of the negative ones. Do like negative pi to negative pi over 2. Okay? Then you have negative 2 pi to, where? Negative 3 pi over 2. Like that. And then you can go dot, dot, dot like that. Okay, that's why I'm going to have you write it in that case. All right. Now let me ask you if you see a pattern on this, because there is a pattern on this. I'm just not going to write it as a formula. But what is the left endpoint? 0, pi, negative 2 pi. So what is that?
K pi.
That's like a k pi, right? That's like k pi an integer. What is the y value? Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So what is it? It's like a k pi over 2 with k being a not integer, right? But generally, we just write it that way, and that's good enough. Once you establish the pattern, you can write it that way if you want to, okay, instead of a formula. Okay, and then increasing goes like this. So you're going to have the things I'm highlighting in blue. We'll just write those down. Okay, so let's start with dot, dot, dot. Let's start with negative 3 pi over 2 until negative pi. Okay, then union, you would have negative pi over 2 to 0. Then you would have pi over 2 to pi. And then let's do one more. You would have like 3 pi over 2 to 2 pi if you carried that out. Then you would have that. Now, if you look at the pattern, they're totally backwards. So on the increasing, the y value is like the k pi. And then the left part of the interval right there, the left part of the interval is like the k pi over 2 like that. That's a fun problem, isn't it? No? Okay. Digs into your trig background a little bit. You know, what students a lot of times think is, hey, the graphing calculator told me the answer anyway. Well, that's not the point. The point is we're learning calculus concepts that tie to this graph. That's the idea. Okay? All right, well, let's go ahead and let's do our break here. Let's see. I gave a couple of diagrams on this. Is stuff we've already talked about, but since we're talking increasing and decreasing, Right, now what this is showing, this graph right here, is you got the graph that I have in black is the function. And one thing you can see on this is it's increasing, and then it ends up having a place where the derivative would be equal to 0. And then I graphed the derivative. So we've talked about graphs of derivatives quite a bit. So notice that if you're increasing, what do you have? You have a positive derivative. So you would notice that all of these values on that derivative are positive. They're all above the x-axis, right? Okay. Right here is where the derivative is 0. That's the value of the derivative is 0. So it's on the x-axis. Then what's happening is the function starts decreasing, that place where I'm highlighting that in blue. And then what does that mean about the derivative? It means the derivative is negative. So notice all of those y values are negative like that. So that's the graph of the function and the derivative. You guys remember talking about functions and the graphs of their derivatives. Okay? We're going to look at that a little bit as we go through some of these. Okay? All right, here's one more illustration of this. This function is doing this. It's increasing until you get to where that dashed line is. So what's the derivative there? Positive. All of those values are positive, right? Then what you have is the function is still decreasing, actually until you get there, like that. So you're increasing, then you're going to start decreasing. So all the derivative values are negative. Then it's going to increase, so all the derivative values are positive. So this is what the sign chart does. The derivative's positive there because you're increasing. The derivative is negative here because you're decreasing. And then the derivative is positive here on that red graph because you're back to increasing again like that. So the graph of a derivative is really what that sign chart's doing for you anyway. Okay? All right. Now, what we're going to jump into here a little bit next is looking at minimums and maximums. We've talked about this a little bit. Then we're going to talk about what we mean by the first derivative test. So here's kind of an idea. This would be a local minimum at C. And if you did your sign chart, notice what's happening on this is the derivative is negative when you're decreasing, right? So that means if you did your sign chart, you would have a bunch of negative numbers. Then the derivative is going to change signs to become positive, so it's going to be increasing. So what you would have, if you did a sign chart on this, you want to write this sign chart down, because if you did a sign chart, you would basically have a critical point at C, and then the result of the sign chart would just go negatives there and positives there. Does that make sense to everybody? That's what we just got through learning. If the derivative's negative, you're decreasing. If the derivative's positive, you're increasing. That's what we learned. Okay? If you look at this graph right here, this is a local maximum. So if you did your sign chart here, what are you going to have here? You're going to have increasing. So what are you kind of signs you're going to have here on your sign chart? Positive. Good. Okay? Then you're going to start decreasing. So what is your sign chart going to tell you? Negatives. Okay, like that. So the sign chart and the graph do the same thing. Okay, you can take a graph and you can see what its sign chart is going to be anyway. And we're going to use that to develop what we call the first derivative test. So if you do a sign chart and the signs change, that means this is going to be a maximum here because it increases then decreases. Okay, right here, this is going to be a minimum because it decreases then increases. So you look for sign changes to identify where you have local maxes and mins. Okay, like that. But the sign's got to change. Does that make any sense? Okay, right? Increasing and decreasing, when they change, is going to generally tell you where you have those local mins and maxes. Okay, all right, everybody good? Okay, so we're going to look at the first derivative test. That's what I just explained to you as the first derivative test. So what this says, if f prime changes from positive to negative, then you got a local max. All you got to do, you don't have to memorize this, just remember that if you have a positive derivative, you're increasing, then it goes to a negative, then you got a maximum. That's what that says. Then if the derivative changes from negative to positive, you have a local minimum. What does that mean? If it has a negative derivative, you're decreasing, right? If it changes to a positive derivative, then you're increasing, so you have a min. Does that make sense to everybody? Okay, it all ties into what we've been talking about, increasing and decreasing. Now, this says if the derivative is positive on both sides or negative on both sides, then there's no extreme. Well, let's look at an example. What if you had something like this? Wouldn't the derivative, you might have a place right there where the derivative is 0, but wouldn't the derivative always be positive on this? So since there's no sign change, that would mean there's no max or min there, okay? Or you could have the opposite case where it's going like this. Well, you might have one critical point right there, but all of these derivatives would be negative, so there's no extrema. So what this is all about, just get in your head that the first derivative, you're doing a sign chart and you're trying to identify places where the sign changes. That's it. That's what it is. Does that make sense? Okay? All right. So we're going to do several things with this first derivative test. Then we're going to eventually, in the next section, get to the second derivative test also that you use. Okay, so we're going to use the first derivative test on this function to identify max or min. Okay, we're going to do calculus. The graph is going to be nothing more than a checking tool to see if the calculus doesn't lie to us. So step one, what you want to do is you want to find the derivative. Okay, we're only going to analyze this from -2 to 4. So go ahead and do your derivative. So that's going to be 10x to the 4th minus 20x to the 3rd minus 30x to the 2nd, like that. Okay, step 2, you want to find your critical points. So what do? You set the derivative to 0, or you see where it's undefined. Is this derivative ever undefined? No, it's polynomial. X can be anything. So what we do is we go ahead and set that derivative equal to 0, and then we got to solve that equation. So this is a pretty straightforward one right here. Okay, this is kind of a good test question because it's pretty basic. It tests your ability on what the first derivative test does. All right, what's your common factor you could pull out of this? 10x squared, always work the lowest exponent. So that would give x to the 2nd minus 2x minus 3 equals 0. And then notice that x squared minus 2x minus 3 still factors, right? So you want to go ahead and factor that further. So go ahead and do that. Okay, so let's see, that's going to be x and x. You're going to have 3 and 1. How do the signs go to get that -2 out of there? Minus 3 plus 1. Okay, you guys good with that? You're going to find out how much you remember once you start doing the homework. Okay, now when you do the critical points, you can do this in your head. You can just write them down now if you want to, but just to remind you of what you're doing is you're setting each factor equal to 0. So tell me in your head what those critical points are. 0, 3, -1. Solve those equations. A lot of times you'll be able to do that in your head. Okay, so those are our critical points, are x equals 0, 3, and -1. Okay, so that's the first part of the first derivative test, is identifying critical points. Now what we're going to do is exactly what we were doing before on increasing and decreasing. We're going to go ahead now and make ourselves a sign chart. So just draw a number line. Be sure you put your critical points in order. I see students not paying attention a lot of times and do that. So let's put the -1, then the 0, then the 3, like that. And then we're just going to do test points on this. Now, what I'm going to do is we're going to work with the factored form. I think you'll benefit greatly from always using the factored form when you analyze the sign. So I'm going to put 10x squared times x minus 3 times x plus 1 there. Okay? Now, here's one thing that we've talked about that you want to take advantage of because you want to do your homework as fast as possible, right? How about that factor right there? Since you have an x squared, what's going to happen there? You're always going to get a positive. So you're going to have a positive there, but those things are going to change, aren't they? So what I'm going to do for that reason, I'm going to save myself a little bit of time, is when I do a test point here like -2, well, that's always going to be positive. Okay, if you plug in -2 there, -2 minus 3 is what? Negative. Then -2 plus 1 is also going to be negative. So what do you have? Positive times negative, so the result's positive. That tells you that the function increases, okay, like that, all right? Then let's go on to a new test point. Let's say -1/2 would be a good test point there, okay? And I'm just going to erase this and kind of write this in. All you got to be able to do this, you can do this in your head, but it's at least a good idea to just do this, okay? So you know that's positive. It always is. This right here is now going to be negative, and then this right here is going to be positive. Agreed?
Mm-hmm.
Okay, everybody see what I'm doing? Okay, so that's positive times positive, so that's negative. So that means the function's going to decrease, okay, like that. Okay, then let's take a test point here, like say a 1. Plug that in, and then you can figure that out from there. So if you put a 1 in for x, you're going to have a positive there, a negative there, and a positive there. So that's negative, okay? So you're still decreasing when you do that then, okay? And then the last thing you're going to have, like if you pick a number bigger than 3, like 4, if you plug that in, it looks like you have a positive, and a positive. So then you're back to a positive result, so you're increasing, okay, like that. So I'm doing that kind of fast, but you can do that pretty much in your head. That's arithmetic. That's what that is. Okay, does that make sense what I'm doing to everybody? Okay. Now, what I do on this is I just figure out, let's go ahead and figure out the increasing. So increasing is going to be there to there. Okay, let's write those intervals out. So that's going to be negative infinity.
Wouldn't it be -2 because you're on an interval of -2 to 4?
What's that?
You're on an interval, so wouldn't you have to start at the beginning of the interval?
Well, increasing, I'm going to do negative infinity to -1.
Okay, I just wondered because it says, f of x, and then it says on -2 to 4, so I thought we were only looking at the function there,
At the top.
All the way up at the top.
where the original function is.
Right, I'm not sure what oh, I got you, I got you. Now, thank you. Okay, yeah. Okay, outstanding. Okay, so you got to pay attention to this, unlike the teacher. Okay, -2 to 4. All right, so yeah. According to the problem, you only want to look at really -2 and then all the way up to 4. Okay, that's the boundary right there. Okay, so you would be increasing from -2 to -1, and then from 3 to 4. Okay, good. That's what you're talking about. Okay, now you're going to decrease from -1 to 0, but you don't just say -1 to 3, because when you have a critical point of 0, the derivative is 0 right there. So you have to break that off into 2 intervals like that. Does that make sense?
And should you have brackets on your -2 and your 4 over there, or no, because we're talking about this?
Because we're talking about, well, yeah, we could, because we're talking, we chop that off. You're correct. Well, you're paying attention to details. Very good. Okay. What he's saying, and he's 100% right on this, is generally the end point of increasing and decreasing is a parenthesis, but this is within a bigger interval. So it would be a place right there where that would be a bracket there, and then you would also have one on the 4. That's kind of picky, but it's right. Okay. All right, does that make sense? It's just part of a bigger interval. Okay, that's an easy one to overlook. Okay, so here's what I do now, is I do this. I just kind of think about in my mind how this graph is roughly going to look to figure out the max and min. So I know what's going to happen on this is I'm going to increase, then I'm going to start decreasing, but then I'm going to keep decreasing, so it's going to have to do something like that, and then it's going to do something like that. What I always do on this is I just sort of draw a graph over the sign chart, and then that'll tell me where the max and mins are. So that means you have a max there, right? So you have a local max at x is equal to -1, okay? Because the sign chart changed from positive to negative. Where is your minimum at? 3. Okay, so you would have a local min. Whoops, I put that wrong. The local min is -3, so that's your min. Okay, and then your max is right here, so you'd have a local max at x equals -1 like that. Okay, so that's what I kind of do is once I get the sign chart, is I just know that this is going to do that, so it's max. How about that? Is that a max or min? Now, notice the sign didn't change. So that means there's nothing there. But then the signs change from negative to positive, so decreasing, increasing gives you a min like that. That's it. So that's what the first derivative test is.
Are the local minimum maximum always going to be a critical point?
Yeah, it's got to be at some place because the critical points are going to define
Where it changes?
where the sign changes. Okay, like that. Because what happens is the critical points, you have a derivative that's equal to 0. So what do you have? You have a tangent line that's horizontal like that, right? And then you do have a tangent line that's horizontal there, but the signs didn't change, so it's not a max or min. Does that make sense? Okay. All right. You guys got any question about that? Okay. All right. That's not too bad. It's a lot of work to do these. And then the graph is kind of showing basically what I came up with anyway. Okay, so let's move on and let's look at this one. We haven't looked at one like this yet. Okay, so let's see. This time I'm going to pay a little bit better attention, -5 to 5. Okay, so let's see. First step, what we need to do is we need to go ahead and find the first derivative. Okay, so we need to do this derivative. That would be a product rule, right? So we need to go ahead and crunch out the product rule and see what goes on with this then. Okay, all right, so let's do that. The first is going to be x to the 2/3. Then you're going to multiply by the derivative of x minus 5. You can do that in your head if you want to save a step. Plus the second. And then times the derivative of the first. Okay, like that. Okay, so if we do that, let's see, we're going to have x to the 2/3 times 1 plus x minus 5. And then when we do the derivative of x to the 2/3, that is 2/3 x to the 2/3 minus 3/3. So that is -1/3. Okay, so that's your derivative. Okay. Now I'm going to clean this up just a little bit here. So before we do anything with this, I'm going to write this as x to the 2/3 plus 2/3. I'm going to leave that as a negative exponent because the factoring is easier that way. So that would be like your first derivative. Okay. So that's a product rule. Now, what you got to do on this now is you got to think of two things on this. You got to think about if that derivative is undefined or where it's 0. This thing is undefined somewhere, and it comes from this little piece right here. Because what that really means is 1 over x to the 1/3, right? Which really means 1 over the cube root of x. So what could x not be there? 0. Okay, so you definitely have a critical point at x equals 0. And again, that's where the derivative is undefined. If you look at my graph, what do you notice at 0? Sharp point, cusp. Okay, so the derivative doesn't exist there. Okay, so we got that. So don't forget that. Okay, that's an easy one to overlook. So we are undefined there. Now what we need to do is we need to take this derivative, set it to 0, and then we need to try to factor something out of this, okay? Otherwise, you're not going to get anywhere on this one. This one does have a common factor, and it's the x. And you do this the same way. A lot of students get in Calc 1, they've never factored anything like this before. That's what you're going to encounter. So what's the smallest exponent? -1/3. That's what you take out. So when we do that, you want to go like this. You want to do x to the -1/3. Then you want to have like a bracket here. And then you want to fill in the gaps, okay, which is not that hard. Think of it this way. If you're thinking about you can always do it this way. You can sometimes do this in your head. You got to think about what power of x you're multiplying -1/3 by to get x to the 2/3. What would go there? 3/3, right? What's -1/3 plus 3/3? It's 2/3, okay? You can do it that way. A lot of times students don't like that way. You can do this way. You could go x to the 2/3, and you could divide it by whatever your common factor is. You can do it that way if you want to. You can't go wrong that way, okay? And then that would be subtract the exponent, so it would be 2/3 minus -1/3. So that's 3/3, right? Does that make sense? Okay. So what has to go here is really a x to the 3/3, but of course that's x to the first, right? Now see, that a lot of times is new to students. You know how to do common factors, but maybe you've never in your life done it with fractions. Well, you got to do it, okay? So you got to be able to handle that. Does that make sense? Okay, I just looked at what do I add negative 1/3 to get 2/3? I got to add 3/3. Just figure it out logically. Now what goes here is this stuff, okay? You took out the 1/3, so what are you left with when you take that out? 2/3 x minus 5, okay? Now you got it factored, but you got to clean it up, okay? So that's a challenge. That's kind of a new challenge that students encounter in this section is with some of the factoring, okay? So let's clean this up. That would be x to the negative 1/3 times x there plus 2/3 x minus, and then that would be, if you multiply that out, that's going to be 10/3 like that equals 0. So I'm just doing a distributive property, 2/3 x minus 10/3. Is that good? Okay, I got a like term here, so I'm going to go ahead and just write that as 3/3 x. That way I'm getting a common denominator. So 3/3 x and 2/3 x is going to be 5/3 x. So you're going to end up with x to the negative 1/3 times 5/3 x minus 10/3 like that equals 0. Okay, now you've got that in a factored form, and then you're going to have the ability now to set those two factors equal to 0 and solve. Okay, you can do that. Now you could also do this if you wanted to. You got a fraction, so you could multiply both sides of this equation by 3 to get rid of it. That's what I'm going to do because it makes it easier, it makes it less work. So what I'm going to do is multiply this side by 3 and multiply that side by 3. Okay, so what you're going to get is 3x to the negative, whoops, don't do that, cancel, because you're distributing the 3 through there. All that's going to do is cancel both of those, leaving x to the negative 1/3 times 5x minus 10 equals 0. Okay, a little bit heavier algebra. Let's pause there and see if you got any questions about anything I did there. The principle you've done before. It's a factoring problem. It's just the fact that we're dealing with fractional exponents. Okay, does that look okay? Okay, all right, and I got rid of the 3. Okay, you don't have to do that, but it's easier. So now what you do is you take each factor and you set each factor equal to 0. Okay, whatever you can do in your head, do in your head. Okay, now the way this one goes is like this. This is really 1 over the cube root of x is equal to 0. Okay, and I want you to think about that equation. A lot of times students overlook stuff like this. Does this equation ever have a solution? Will this thing ever be 0? No. What you want to get in your mind is there's only one way to make a fraction 0. You know what that is? Is the numerator is 0. And that's never 0. That's never going to change. In fact, you're undefined at 0 anyway there. So there's no solution on that. How about that one? That's 2, right? Okay, you can add 10 to both sides and divide by 5. That gives you 2, so that gives you another critical point. Okay, so this one has no solution. I mean, you could do this. You could cross multiply. Look what happens if you cross multiply. You get 1 equals 0. The math doesn't lie. It always works out. It'll tell you there isn't anything there. Okay, and then this, of course, would be 5x equals 10. Divide by 5, you get x equals 2. You can do that in your head, though, and that's fine. So then that would mean your second critical point is at x equals 2. So again, what you'll find in this section some is the algebra is going to be a little more intense than maybe that you're used to from time to time. Okay, so like I always say, calculus, you're going to get really good with your algebra as you continue to go through. We're going to get pretty algebra heavy in this section. Okay, so now what we're ready to do is we're ready to do our sign chart. So our critical points are x equals 0. That was a place where the derivative was undefined. Graphically, that's going to be represented by that cusp. Then you have x equals 2, like that. And then we're ready to just look at our derivative, and we're ready to do a sign chart on this then, okay? So what I'm going to do on this is I'm going to look at my derivative. I've already kind of lost stuff on here. Where's my derivative? It's always a good idea to have that down. Where's my factor? You can go all the way here if you want to, by the way. You can just plug into the simplified factored form and it'll work out. Okay, so let's just do that. Okay, so we're going to work with, let's actually write this as 1 over the cube root of x. And then let's write this as just 5x minus 10. Okay, you could even do this if you wanted to. You don't have to, though. But you could factor a 5 out of that, so you'd have x minus 2. Okay, like that. Okay, then if you do your test points, it's going to kind of go like this. So if we start like with, now I got to pay attention to my interval here, so you corrected me on that, -5. Okay, we got that. Okay, so if we take like a -1 and plug it in here, okay, what are you going to have? You're going to have 1 over the cube root of -1. Who cares about the 5? It doesn't matter. Then you're going to have -1 minus 2. Okay, so that's what you're going to work out. When you do this, what's the cube root of -1? That's -1. So that right there would be a -1 times 5 times -3. Okay, that's positive, isn't it? So that means the function's going to increase right there. That's the idea. Okay. So you do whatever arithmetic you need to do. Now plug in a 1. Okay. Again, we're going to plug in right here. So that's going to be 1 over the cube root of 1 times 5, although the 5 doesn't matter, and then 1 minus 2. Okay. If you work out the details, you have a positive times a negative. So that's decreasing right there. Now, I'm not going to spend a lot of time on the arithmetic because you're going to get that down once you start doing problems. You do whatever you have to do as a student. Work it all out if you have to. Okay, go to 3. So we're going to go 1 over the cube root of 3 times 5 times 3 minus 2. What's that? It's positive, right. Everything's positive. Cube root of 3 is positive. Everything's positive. So that's positive. So that means that you're increasing like that. So we got our sign chart put together. Okay? Right? Everybody with me what I'm doing with that? The arithmetic's the boring part, but you got to deal with it. Okay? As it goes. Now we're ready to write the answer. So basically what we have on this now, so it looks like we're increasing here to here. Now you got to pay attention to this interval they gave you. So you're going all the way out to 5. And then you're going all the way out to -5. So those are the endpoints. So you would be increasing from -5 to 0, but you'd have a parenthesis on 0 because the derivative doesn't exist there. Okay, and then you would have union 2. You would use a parenthesis there because the derivative is 0 there. And then you would go to 5, and then you would have a bracket because that's a part of a bigger interval. Does that make sense? Okay. Decreasing 1 place right in there. That's between 0 and 2. And that's going to be 2 parentheses from 0 to 2 like that. Okay, so that's what that tells you. Okay, and then what you have is if you look at the graph, without your graphing calculator, it would kind of be kind of like this then. I always just do this. I know that I'm increasing. I know the derivative doesn't exist, so something's going on there, sharp point or something. Then I'm decreasing, then I start increasing again. So where is your maximum?
0.
At 0. Okay, so you have a local max at x equals 0. Where's your minimum?
They have that backwards.
What's that?
You got that backwards.
Oh, I did that last time. I'm not paying attention to the...
Let's hit the local min first.
Yeah, why did I do that? I don't know. Okay. Local min here, x equals 2. Local max here at x equals 0. Okay? And see, that function is defined at 0. If you go all the way back to the original function, x to the 2/3 x minus 5, you're defined at 0. So you have a point at 0. You don't have any discontinuity at 0. It's continuous there. Okay? All right, what do you think of that? Okay, a little algebra heavy. Okay, that's kind of what we're getting into here. Okay, any questions about anything? Okay, now one thing you can do on this is I want you guys to be sure you know how to do a sign chart as much as possible without a calculator. If you're doing your homework and you get in a pinch, which you're going to do sometimes, get your calculator out and graph it, and that'll tell you what the sign chart is. You see what I mean? When I look at this graph, I know that I'm going to have plus, minus, plus. Everybody see that? You guys know what I mean by that? Tell me. Because what you have is you have a positive derivative, right? Negative derivative. positive derivative. The graph tells you the sign chart, okay? So you want to be able to do that arithmetically, but you want to be able to check that with your calculator too. You're going to get into a situation where you need to save a little bit of time from sometimes. Okay, let's do a inverse trig now and see what goes on this one. Just for something a little bit different here. We want to try to get in as many different types of functions as we can do here. So let's go ahead with this one, and I'm going to start by doing the first derivative. Okay, inverse tangent shows up a lot in calculus. It'll show up a lot in Calc 2. What's the derivative of the inverse tangent? Have you got that memorized? 1 over 1 plus x squared, right? Okay, good. All right. So that's 1 over 1 plus x squared. And then the derivative of x to the third is 3x squared. Okay, so we have that. All right. Now, two things you got to pay attention to. I'm trying to stress the undefined because that's where students forget. Look at this derivative. Is that derivative ever undefined?
Yes.
Yes, because there's a
No,
no.
you can't have a -1.
Yeah, right there. If you square something, you're going to get a positive there, right? Or you could get 0, but 1 plus 0 is 1. When I look at that, I know that that will never be 0. Never, ever. That's a complex number anyway. Like if you set x squared plus 1 equals 0 and solve, you get complex number. So it's never undefined. So that means we're going to go ahead and set that equal 0. Does that make sense? Do not forget about looking where the derivative doesn't exist. In this case, that means that the derivative always exists. So what we move on now when we do the critical points is we do 1 over 1 plus x squared minus 3x squared equals 0. Okay, so we now want to focus on solving that equation. And you're going to solve equations like crazy when you're working with this section. So let's talk about how we would do this. And there's several approaches. What I'm going to do is move the 3x squared to the other side like that. Okay? You could cross multiply. You could also clear the fraction. It's up to you. I'm just going to clear the fraction. So I'm going to multiply this side by 1 plus x squared. And I'm going to multiply that side by 1 plus x squared. So if I do that, looks like I've got 1 is equal to, and then I've got to multiply this out. So that's going to be 3x to the second, and then plus 3x to the fourth, like that then. Okay? Okay, how's that look? Because you need to ask questions if you don't understand the algebra, because that's the biggest part of this section for a lot of students is that. Okay, now what? What do you think? One side equals 0. One side equals 0, and you hope it factors. Okay, that's the hope. All right, so we got 0 equals 3x squared. Oh, let's write it kind of in this order. Okay, we have 3x to the fourth. Yep. Like this. It's just easier to factor if you write it in this form. So 3x to the fourth plus 3x squared, and then minus 1 is equal to 0. Okay? All right. So let's see if this one will factor. I think it might. So I'm going to draw two parentheses and do this. This is a trinomial. The first term is going to have to be what probably? 3x squared and x squared. Can't be anything else. The last term, that's nice. It's got to be a 1. And then you're going to try to get these terms to add up. Is that going to factor or not? I think that's going to be a little bit problematic on that, isn't it? So I think we may have to go technology on this one. Yep. I'll show you what to do, though. This is important. So there's no way that you can get that term to add up to 3, so it doesn't factor. Is everybody with me on that? It does not factor. You can try all day and it won't factor. Okay? We also can't use the quadratic formula necessarily. I mean, you could because this is what's called quadratic reducible. So what we're going to do is we're going to take a technological approach to this problem. Okay, so get your calculator out and let me show you how to handle this when this happens. So what we find is this thing right here, to solve this equation, you really need technology. You need some technology. Okay, so what you want to do is get your calculator out and then you can run through this with me and I'll show you what we'll do that, because this will happen every now and then. What you want to do is, the first thing you want to do is you want to get your derivative, or I'm sorry, get the equation that you're trying to solve. The equation we're trying to solve is this right here. We're trying to figure out where that's 0. So what you want to do is you want to go ahead and just in y1 put in 3x to the 4th, and then plus 3x to the 2nd, and then minus 1. And
get on a radian.
it doesn't matter. The radian or degree won't make any difference on this, okay? So let's go ahead. Now what we're doing is, again, I gave you this interval, -1 to 1, right? Okay, that tells me you want to get that in your calculator, and then you want to go, let's set up our window. So when we do our window, you want to go -1 to 1 because that's a part of the problem. You can scale by whatever, we'll say like maybe 0.5. And who knows about y? I have no idea. I'm just going to try something like -5 to 5 and see what I get. I'll adjust it if I need to. So let me just try that and see if I got a graph. And I'm looking for something on this. So this is the technological approach to solving the problem. Okay, so I got everything I need. There's my window right there. If you need to look at my viewing window, that's what I used. Okay? All right, so we want to get the graph. Everybody good there? Now, what are you doing in this graph? Okay, you're looking for where it's equal to 0. How many places does this graph have a y value equal 0? 2. There and there, okay? Now, you want to get this as close as you can. If you don't know this, we maybe have done this in this class before, you do this. If you want to find those pretty specifically, you can go like this and write this down if you need to. You can go second trace. I'll write down the steps as you go. You can write it down if you need to. You may already know how to do this. I don't know. So you can go second trace. You can go option 2, which says find the 0. Okay, like this. All right. Now what I'm going to do is it's going to ask for a left bound. Let's find this 0 right here. I have a sneaking suspicion they're the same. Okay, and that's because this is an even function. I'll explain that in just a minute. Okay, so I'm going to get pretty close to there. Okay, that's a left bound. Just be to the left of it. Press enter. Usually a line comes out or a triangle. Ask for a right bound. Now press your right cursor key until the little spider gets a little bit to the right of it, like this. Okay, that looks like a good right bound. Press enter. So then when it says guess, press enter again. And there's your 0, about 0.51. Okay, so we're just going to write that as 0.51, and then we'll say that's -0.51 like that. Okay, that's how you do that. With technology, you can do the 0 command because you're trying to find basically where that graph crosses the x-axis. Okay, does that make sense? Okay, you can do that if needed, and you will need that every now and then. Some problems you've got to solve equations with technology. You have to. Okay? Okay, now let me ask a question on this. I knew that was -0.51, not because of the way the graph looked. You know how I knew that? That's an even function. Do you understand what I mean by that? Okay, it's symmetrical about the y-axis. Okay, that's an even function, so that means that it's symmetrical about y, so if that's 0.51, that's -0.51. That's how I knew that, see? Okay? So now what I'm going to do, now this is a great technological problem, so we're going to go ahead and do our sign chart, but we're going to use our calculator 100% for the rest of this problem since we already got it out. Let's go ahead and let's draw the number line, and let's see our critical points. What we have then is we have about approximately plus or minus 0.51. Those are the two critical points we have. So I'm going to put like 0.51, these are approximate, and -0.51 like that. Okay? Now see what I just did is I just graphed that derivative, okay, right there, okay? So if I was to go through and do this now, if you look at this, let's go ahead and let's do the rest of this on the calculator. So we got the solution of that problem. Now what I'm going to do next is I'm going to have you put in this derivative in your calculator. So this is an alternative technological approach to doing this problem. So if you want to just do the sign chart like this, you could. Okay, we could go through and we could graph 1 over parentheses and then 1 plus x to the second. Okay, like this, and then minus 3x to the second. So if you ever get into a crunch on your homework, I don't want you to do this on every problem, but if you want to graph your derivative, you can get your sign chart by doing that. Okay, so I'm just going to do that kind of in the same window. Let's see what we get. Okay, that right there will tell you your sign chart. Okay, and this is super important. Okay, can you tell me what the sign chart's going to say? That's a critical point, that's a critical point. How are the signs going to go? The derivative is what there? Negative. Okay, don't think about tangent line. The derivative has negative values, right? Below the x-axis, above the x-axis. Your sign chart's going to go negative, positive, negative. Agreed? Okay, that's what you would do if you did the sign chart by hand. That's what you would end up getting. So you can save a little bit of time by doing that. Okay, so it just kind of goes like this then. These are negative values, these are positive values, and so forth. So your sign chart's going to go negative, positive, negative. Okay, now we're ready to answer the question. Okay, so what we would have, we do have an interval, it looks like, from -1 to 1 on the problem. So it looks like what we're going to have is we're going to be decreasing here, increasing here, then decreasing again, and then we can write those intervals out. So we're going to be, first of all, increasing from here to here. Okay, so that's just going to be from parenthesis -0.51 to positive 0.51, okay, with parentheses. Decreasing is going to be starting at -1, including it because it's a part of a bigger interval, and then to -0.51 with a parenthesis. You're rounding. Then union 0.51, comma, and then 1 with a bracket like that. Okay? Now we can do the max and min pretty easily, so if you just draw a graph, this is what I always do. I just draw a graph over this. You're going to decrease, you're going to increase, then you're going to decrease like that. Okay, so where is your minimum? Right here. There's your minimum. Okay? So that minimum is at x equals -0.51. Where's your max? Right there. Okay, so your max is at x equals positive 0.51 like that. Problem done. Okay, and I put the graph, I think, on your handout. This is just, that's -0.51, that's your min, and then here's your max, so it's real easy to check and verify this by looking at your graphing calculator. Okay, so I wanted to get in a couple of examples where technology comes in handy. You guys see what I'm talking about by that? The reason I did technology is because this equation right here, you couldn't factor it. You could actually do that with a technique that's called quadratic reducible and use quadratic formula, but I'm not going to go there. I think it's just as easy to do technology on that problem. Okay? Okay. Any questions? Okay. A lot of repetition. Now we're going to go to concavity and kind of finish up class by talking about concavity a little bit and what inflection points are. Okay? So I want to kind of talk about what happens with the idea of concavity. All right, so a couple of things on this next page. I'm not going to talk about that theorem on that. I want to just kind of look at having you maybe write out a couple of notes to yourself, because this is pretty important on page 10. So concave up means the graph looks like this. And you want to maybe just make a little diagram somewhere on your notes so that you have this. Concave up would be a place on the graph where it's kind of like a U shape going upwards, okay? Or it could even be like half of that. It could be something like that. That's still concave up. Or it could be something kind of like that. That's the rough shape of the graph, okay? We call it concavity, okay? And that's kind of how that looks. I always think of concave up as a smiley face. That'll be a visual that will come in handy as I teach you how to test for concavity. Okay, concave down would just be the opposite of that. So what you're going to have on this is concave down would just be almost like a parabola going down or something like that. Or it might be half of that. It might look like something like that. Or it might look like that. Those are kind of the possibilities for concavity. Okay, I think of concave down as like a frown. Okay, like that. So that's my picture that I use to kind of help students remember that. Okay, so here's what happens on this. Now this is what you want to try to get. This is pretty abstract, so we want to try to get the idea and see if this makes any sense to us. Okay, in this diagram right here, you would be concave down, right? Okay, and then you're going to change to concave up. So it's kind of like you're frowning and then you're smiling. Now I want to show you what happens on this. Okay, the derivative right there is positive. Do you agree? In fact, the derivative is always positive there, right? But what's happening is it's changing a certain way. Okay, think about that. That's a big slope, agreed? That's a small slope, agreed? So what's happening is the derivative is decreasing. In other words, the slope of the tangent line is decreasing. So what you're going to end up doing for this concavity test is concave up is basically a place where the derivative is positive, but it decreases. Okay? That's concave down. Now concave up in this shape, what you're going to have is positive derivative, agreed? But what's happening to that derivative? Getting bigger or smaller? Bigger. Small slope, big slope. So that's saying that that derivative is increasing whenever you're concave up. Does that make any sense? Okay, you're looking at the slope of the tangent lines and you're seeing how they change. Okay? So that's kind of roughly the idea on that. So let's go to the next page and kind of formally give the definition of this then. Okay, these are kind of some different situations we have here. So when we have an inflection point, okay, that's going to be a point on the function where the concavity changes. So sometimes your concavity is going to change from up to down or from down to up. Okay, so if you look at this diagram right here, your concave down here, that's kind of like you're frowning, and then your concave up there, now you're happy again. Okay, your inflection point would be right there. And it's going to turn out that that inflection point is a place where the second derivative is equal to 0. And that's because of how the first derivative is changing. You can figure out, by taking a second derivative, you can figure out where the first derivative increases and decreases. So you're going to work with second derivatives on concavity. Okay, this would be the same thing. You're going to go concave up, then you're going to change to you're still concave up right there. Okay, so that would be a place where the second derivative is 0, but it's not an inflection point. Okay, the concavity did not change, so it's not an inflection point. Okay, so you would end up having any place where the concavity changes from one to the other, then you're going to have an inflection point. However, what happens on this one is, in this case, the second derivative doesn't exist because that's a vertical tangent line. And then here's one last possibility. You're concave down, you're still concave down, so that's not an inflection point like that. So what you want to kind of get in your mind is what concavity looks like, just roughly, and then we're going to kind of look at this last thing here to kind of finish up here today. So here's how you test for concavity. And it's actually a real simple thing to do, is if you want to find where something's concave up, you just determine where the second derivative is greater than 0. Okay, that's really abstract, but I'll try to explain that one more time. You're concave down wherever the second derivative is negative. So you're going to work with the second derivative when you're dealing with concavity. All right, now I want to explain one more thing, and then that'll wrap us up here today. So I want to go to this diagram again. I want to see if I can get you guys to understand this okay, why it's the second derivative. Okay, this shows this pretty well. Okay, this is what I was showing before. This is concave down. Everybody agree with that? Frown. Okay, what's happening here is the first derivative is changing. The second derivative is a measure of how the first derivative changes. It's another rate of change. So what's happening on this thing is, that thing is, what it's doing is the value is getting smaller. The value of that slope is getting smaller. So what that means is the first derivative is decreasing. So that's going to be a place, whenever you're concave down, that's going to be where the second derivative is negative. When we decreased, wasn't that a place where our sign chart was negative today? So we're doing a derivative of a derivative. So if that derivative is decreasing, the second derivative is going to be negative. Does that make any sense? That's a tough one, I think, for a lot of students. Okay, now if you're concave up, what is the derivative doing? The derivative is getting bigger, agreed? Okay, so the derivative is increasing, okay? If something increases, the sign chart gives you a positive, right? So what you would have on this is the second derivative would be positive. So what you're going to find, and I'll show you this one thing to help you remember this. This will be kind of what you want to use until you kind of get this a little bit better in your mind. These little diagrams right here is going to tell you a lot. So if you're concave up, I always tell students on concave up, just refer to this smiley face. And that means it's a positive. That just means the second derivative is positive. I sometimes tell students to put a tattoo, like a F double prime tattoo on its cheek, to help you remember its second derivative. Then if it's concave down, what you do is it's frowning. It's got negative eyes. So that just means the second derivative is going to be negative. So that diagram tells you how to analyze concavity. So we'll work on that next time. I thought we'd get there today, but we're not. And this is a long section, so we'll wrap this up next time.